Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the most haunting and beautiful questions science has ever asked. Is time travel truly possible? Could we ever step beyond the moment we're in, drift gently into the past that shaped us, or leap toward the future still waiting to unfold? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each of us suspended in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the strange, shimmering world of physics, where imagination and reality blur, and where time itself begins to bend in ways both mysterious and familiar. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. It begins on a cold, misty night, the kind where the air feels thick enough to remember. A teenager steps off the curb, distracted by the flicker of a streetlight just as a car's headlights burst through the fog. There's no time to react, no chance to move. And then, out of nowhere, an older man rushes forward, pushes the young stranger aside and takes the impact himself. When the confusion clears, there's only the sound of rain and the dull echo of sirens approaching. The boy survives. The older man does not. Later, under the weak fluorescent light of a police station, an officer hands the boy a small weathered envelope found in the victim's pocket. It bears the boy's name, written in familiar handwriting. Inside are two simple words: study physics. The years pass. The boy, now a man, does exactly that. Perhaps out of guilt, or perhaps because the mystery of that letter burrowed deep into his mind like an unanswered equation. He becomes a physicist, obsessed with the nature of time, and one day, late in his career, he finally succeeds in building the world's first working time machine. As the machine hums to life, he feels a flicker of recognition. He reaches into his desk drawer, takes the old letter, still framed, still yellowed by years, and places it back into its original envelope. Then he sets the coordinates. A cold, foggy night. A road glistening with rain. You can imagine the rest. The rush forward, the blinding light, the sound of tyres against wet asphalt, and a man stepping out of the shadows just in time to push a boy to safety. He dies where he once stood. The circle closes perfectly. At first, it seems almost poetic, tragic, but neat. Yet beneath that symmetry lies a labyrinth of impossible questions. Who wrote the letter? If the older man simply delivered the same note he once received, then the letter has no origin at all. It exists in a loop with no beginning. An echo trapped between two moments forever feeding itself. Physicists call this the Bootstrap paradox, but it feels less like a problem and more like a whisper from something ancient. A thought born out of nowhere, existing only because it already existed. Then comes the restoration paradox, a quieter question that lingers like fog around the edges. If the letter passes through time over and over, does it age? Does the ink fade with every loop? Does the paper remember each cycle of its impossible journey? Even in an endless circle, matter still obeys the slow breath of entropy. Perhaps even eternity wears out. And what about choice? Did the young man ever really decide to study physics? Or was he always destined to do so because his future self had already set the path? This is the predestination paradox, and it feels strangely familiar. The sense that life sometimes moves like a dream already written, each decision guided by a hand you can't quite see. But there's another darker version, the ex nihilo paradox, meaning from nothing. It asks, where did the first idea come from? the design for the time machine, the spark of curiosity, the courage to try. If every cause has an effect and every effect a cause, where does the first spark begin when the chain loops endlessly? And finally, the one paradox that makes us flinch. The auto-infanticide paradox, the idea that you could travel back and undo your own existence. But nature, it seems, does not allow such self-erasure. In this story, the older self cannot hesitate or change his mind. If he didn't step into the road, the boy would die, and then there would be no older self to go back at all. The loop would collapse. The universe would correct itself, sealing every hesitation like a self-healing wound. Each of these paradoxes pulls gently at the threads of our understanding. Together they form a web where logic bends but never quite breaks, where cause and effect chase each other in circles until they become indistinguishable. If you listen closely, this story isn't really about time machines at all. It's about fate, memory, and the quiet suspicion that life might be more circular than we admit. It's about how the things we do today may already be written into the pages of tomorrow. The physicist's letter sits forever in that impossible moment, halfway between the past that created it and the future that delivered it. Like a thought echoing between two mirrors, it has no origin, and yet it exists completely. And maybe that's what time itself is, not a straight road, not a clock that ticks forward, but a conversation between what was and what will be. A dialogue that never truly ends. If we follow the thread a little further, the story begins to widen. The question is no longer just what happened to one man, but what happens to all of us, caught in the slow current of time. What is this invisible river that carries every life forward, never backward? And could we ever learn to step outside it, even for a moment? Our quiet exploration now turns to that river itself, and to the deeper mystery beneath every ticking second. What is time, really? Time is the one thing you can never touch, but it touches everything. You live inside it, breathe through it, measure your whole life by it, and yet most of us don't really know what time is. We speak about it as though it were a river flowing steadily forward, a quiet current that carries us from moment to moment. We say we spend time, we lose it, we waste it, as if it were a possession, something that can slip through our fingers. But maybe time isn't something we move through. Maybe it's something that moves through us. If you listen carefully, the rhythm of time hides in everything, in the way your heart keeps its beat, in the tide that pulls the ocean back and forth, in the way light travels from a distant star reaching your eyes years after it left its home. Every one of those patterns is a reminder that time isn't just a human invention. It's part of the structure of the universe itself, invisible but constant. For centuries, we believed time was absolute, the same for everyone, everywhere. You could count seconds on Earth and trust that the same seconds ticked away on the Moon, on Mars, or beyond. The universe, people thought, kept a single perfect rhythm, like a vast celestial clock. That was the world of Newton. Simple, predictable, beautifully mechanical. But then came Einstein, and everything changed. Einstein showed that space and time are not two separate things, but one continuous fabric. Imagine an enormous sheet of invisible silk stretched out in all directions, perfectly smooth, perfectly still. That is space-time. Every planet, star, and galaxy presses down into it just a little, and where the fabric dips, other objects naturally slide inward, not because of any invisible rope pulling them, but because the space itself curves. That's what we call gravity. Not the force, but the gentle bending of the stage on which everything moves. When you picture it like that, you can almost feel how everything is connected, how matter tells space-time how to curve, and space-time tells matter how to move. It's like an endless dance between weight and motion, between the physical and the invisible. But here's the astonishing part. Because space and time are woven together, when one bends, so does the other. A star's gravity doesn't just pull on nearby planets, it stretches the seconds themselves. Time runs a little slower where the pull is strong, a little faster where it is weak. Near the surface of the Earth, your watch ticks ever so slightly slower than one sitting on a mountaintop. The difference is tiny, billionths of a second, but it's real and measurable. We tend to think of time as something steady, like the ticking of a metronome. But Einstein showed it's more like a fabric that can stretch and twist, or like the surface of a drum that vibrates when touched. Under the right conditions, even time can ripple. If you could somehow look at the universe from the outside, as though standing beyond all of it, you might see space-time not as something flowing, but as something complete. Every moment, past and future, all existing together, forming one vast four-dimensional shape. Physicists sometimes call this the block universe. It means that yesterday, today and tomorrow are all part of the same structure. They all exist, just in different locations along the fourth dimension we call time. That might sound unsettling at first. If the future already exists, what does that mean for choice? For free will? For hope? But think of it this way. When you look at a map, every destination is already printed there. Yet your path across it, the route you take, the way you wander, is yours to make. The map doesn't tell you how to travel. It only holds the possibility of every journey. Einstein once wrote that the separation between past, present and future is only a stubbornly persistent illusion. He didn't mean time wasn't real, only that our experience of its flow might be something our minds create, not something written into the laws of nature. We feel time passing because we are creatures built to notice change. We remember what was, but not what will be. So it feels as though the universe is moving forward, when perhaps it's simply unfolding, all at once. Imagine a movie reel, coiled up in your hands. Every frame of the story, the beginning, middle and end, already exists on that strip of film. But you only see it come alive when the light passes through, frame by frame. The film itself doesn't move. You do. That's what it might mean to live inside time, to be the light passing over the frames, bringing the story to life. And still, there's another question. If time doesn't truly flow, why does it feel like it does? Why do we grow older? Why do moments fall behind us and never return? To answer that, we have to look at something that isn't just physics, but something deeper. The one law of the universe that never bends. The law of increasing disorder. When you drop a glass, it shatters. When ice melts, it never reassembles itself into the same cube. These aren't just accidents, they're nature's quiet rule. Physicists call it entropy, a measure of how much disorder there is in a system, and entropy always increases. It's what gives the universe direction. The arrow of time, that sense of before and after, is born from entropy. In a way, it's not time that moves forward, but disorder that grows. Every star that burns, every breath that leaves your lungs, every thought that fades from memory, all a part of that steady drift from order to chaos. It's what makes time feel like it has direction, even if the equations say otherwise. But there's something poetic about that too. Entropy isn't just decay, it's the reason things happen at all. Without it, nothing would change. No stars would shine, no planets would cool, no lives would unfold. The universe would be frozen, silent, perfect, and completely still. It's the imperfection, the movement toward disorder, that lets time exist as we know it. So maybe time isn't a river that flows from past to future. Maybe it's more like a great landscape already shaped, and we are the travellers moving across it, guided by the whisper of entropy and the rhythm of our own hearts. And when we stop and look around, we realise that every second, the one you're living in right now, is a place. You're not rushing through it. You're standing in it. A single, luminous moment suspended in a universe that holds every other moment close. As we drift further into the story, we'll see how this strange, flexible fabric of space-time opens the door not only to wonder, but to something even more mysterious, the possibility of travelling through it. For if time can stretch and curve, if it can slow and quicken, then perhaps it can also fold, bringing tomorrow and yesterday close enough to touch. Our path now carries us toward the experiments and real-world clues that show this isn't just imagination, but measurable truth. We'll meet the astronauts, the clocks, and the particles that have already taken the smallest steps into the future. Close your eyes for a moment and imagine standing on the bank of a river. You can see the water slide past, slow and silver beneath the moonlight. You know that the water at your feet was once further upstream and that it will soon drift farther away. It feels like a perfect image of time, something that carries you forward while everything behind fades into distance. Yet that's only how it feels. The water isn't gone, it's still part of the river, still connected, just somewhere else along the curve. What if time is the same way? Not vanishing, not truly moving, but simply existing in a shape too large for us to see all at once. Einstein's view of the universe suggested exactly that. In his equations, nothing in nature insists that the past disappears or the future waits to be built. The laws of physics treat every moment with equal weight. A supernova that flared 5 billion years ago and a thought you'll have tomorrow both sit quietly within the same vast fabric of space-time, like two notes written on the same sheet of music. We experience them separately only because we can't read the whole score at once. This picture, sometimes called the block universe, can feel both comforting and strange. Comforting because it means nothing is ever truly lost. Every sunset you've watched, every word you've spoken, every heartbeat of someone you loved, they're all still there, fixed in their rightful place in the grand pattern. Strange because it means the future might be just as real as the past, waiting for your consciousness to reach it. We think of time as something that flows, but in this view, we're not being carried down the river. We're walking through a landscape that already exists. Imagine for a moment that the whole universe could be paused and displayed all at once. Every particle, every flicker of light, every heartbeat frozen in its precise position. It would look something like a four-dimensional sculpture, height, width, depth, and a fourth axis representing time. You could trace the path of a single atom as a glowing thread, twisting and looping through that sculpture. Or follow the long, winding lines that mark your own life, from the first flicker of awareness to the moment when your story closes. These paths are called world lines, and together they form the intricate weaving of everything that has ever existed. In that sense, you're not just living in time, you are time. Your body, your thoughts, your memories, even the sound of this sentence in your ears, all are sections of a single shimmering thread, existing simultaneously across the dimension we call duration. You are the river, the current, and the traveller, all at once. And yet, if time is a static landscape, why do we feel it move? Why does the present seem to sweep across the map, erasing one horizon and revealing another? The answer may lie less in physics than in perception. The human brain isn't a passive recorder of events, it's an artist, constantly stitching moments together to create the illusion of flow. Think of an old film projector. Each frame is still, silent, and complete. But when the light flickers through 24 of them every second, motion appears where there was none. In the same way, our consciousness slides from one moment to the next so seamlessly that we never see the flicker. We believe in motion, in the continuous passage of time, but perhaps it's only the speed of our awareness creating that blur. There's something deeply human about that. We are storytellers by nature. We need beginnings, middles, and ends. So we weave the moments of our lives into a narrative, believing the story moves forward. But to the universe, every chapter already sits open, every page already turned. The story doesn't move, the reader does. Even knowing that, it's hard not to feel the tug of time. There's the sound of a clock somewhere nearby, or the shifting of light through a window, reminding you that moments keep unfolding. Entropy, the gradual spreading of energy, the quiet drift toward disorder, gives time its heartbeat. It's why eggs break but never unbreak, why we remember the past but not the future, why candles burn down instead of up. In the block universe, everything is fixed, but our perception moves from lower entropy to higher, like climbing a staircase of increasing disarray. It's that climb that gives us the sense of direction. If you think about it, we never actually witness time itself, only change. The turning of planets, the fading of stars, the creases that gather at the corners of our eyes. Time isn't the actor, it's the stage on which change performs. Without change, time would be invisible and perhaps meaningless. There's an old analogy that physicists like to use. Imagine a book, bound and finished, its story complete from first page to last. All the characters, all the events already exist in those pages. But as you read, you experience suspense, surprise, emotion, as though the story were being written right now. It isn't, of course. The ending has always been there. Yet for you, the act of reading transforms a static object into a living experience. The universe may be just like that book. Every page already exists, but consciousness is what turns the pages. This perspective doesn't erase free will, though it changes how we see it. It may be that all possibilities already exist, and what we call a choice is simply the moment when one path in the landscape becomes illuminated by our attention. Free will isn't about writing a new future, it's about discovering which of the existing futures we'll inhabit. The terrain is drawn, but the journey remains our own, and that journey is mysterious. We can never step outside time to look at it directly. Every observation, every measurement happens from within. Even Einstein, when he described time as relative, was still part of the same tapestry. He once remarked that the past, present and future are illusions, but they are stubborn ones. Perhaps we need that illusion. Without it, there would be no music, only the frozen arrangement of notes, no laughter, only air molecules suspended in place, no heartbeat, only a shape that never pulses. The illusion is what lets life unfold, so maybe time doesn't flow, not really. Maybe it simply is, quietly holding every event that ever was or will be. What flows is us, the small luminous awareness that moves along the current, painting motion onto stillness, finding meaning in the unfolding of what already exists. And maybe that's enough. If we follow the thread a little further, we'll discover that this illusion, this slow drift through a timeless landscape, can be tested. There are clocks, satellites, and even particles that prove time doesn't beat the same for everyone. The river changes speed, thickens and thins, depending on where you are and how fast you move. In the next step of our journey, we'll look at the quiet experiments and human stories that show this illusion isn't just philosophy, c'est-à-dire, it's measurable reality. If you leave a cup of hot tea on a table, the steam rises, the warmth fades, and soon the cup is cold. No matter how long you wait, it never reheats itself. If you drop a porcelain plate, it shatters on the floor, but it never leaps back together again. It seems so ordinary we barely question it. Yet this one-way pattern is one of the deepest mysteries in all of physics. Why does everything in nature unfold from order toward disorder, from energy concentrated to energy dispersed? Why does time itself seem to have a direction? To understand that arrow, imagine film running backward. The tea grows hot again, steam flows down into the cup, shards of porcelain leap into your hands and seal seamlessly into a perfect plate. Nothing in the fundamental equations of motion forbids this. The same rules that make heat spread and planets orbit would also allow them to reverse. But in the real world, It never happens. There's something about the way matter and energy behave on a large scale that gives the universe a preference. Forward. Physicists call that preference entropy, the natural drift from order to disorder. It's not a curse. It's simply how probability behaves when countless particles move and collide. If you toss a handful of coloured beads in the air, they'll land in a random pattern, not neatly sorted by colour. There are infinitely more ways for them to be messy than for them to be arranged. The same is true for every atom in the universe. The number of possible disordered states vastly outweighs the number of ordered ones. So, as time moves, disorder wins. Not by law, but by likelihood. Entropy gives us the arrow of time. It explains why ice melts but water never freezes itself mid-air, why smoke spreads through a room instead of gathering into a neat cloud, and why memories form in one direction only. When you remember something, your brain builds order, a pattern of connections, out of a previous state that was simpler. You never remember tomorrow, only yesterday, because your mind rides the same current as the rest of the cosmos, from less complex to more, from smooth beginnings to tangled stories. If you trace that arrow backward, you eventually reach a question that feels both cosmic and intimate. Why was the universe so ordered in the first place? At the beginning of everything, during the event we call the Big Bang, matter and energy were compressed into an unimaginably small, dense state. It should have been pure chaos. Yet in some way, it was also perfectly smooth, low in entropy, like a tightly drawn bow, ready to release all possible futures. That tension, that low entropy beginning, is what allows time to stretch outward today. Every sunrise, every heartbeat, every drop of rain cooling on a windowsill, all a part of that long unwinding from the universe's first breath. Entropy is often spoken of as decay, but it's more like growth. It's the way energy spreads to fill space, the way stars shine by releasing their stored fire, the way living things harvest difference and turn it into motion. Without entropy, nothing would happen. The arrow of time would vanish, and the universe would freeze into still perfection. Change and life both require imbalance. A hill for the river to run down, a spark to fade, a story to move forward. You can even feel entropy in your own body. The warmth of your skin flows outward into the air. Muscles tire because the energy that once drove them becomes soft heat. Even your thoughts, those flickers of electrical order in the brain, slowly dissolve as the patterns fade. It might sound melancholy, but it's also what connects you to the stars. Every second, your body releases energy into the wider world, just as the sun does, contributing to the universal rhythm of spreading light. Some scientists have wondered whether the arrow of time might one day reverse, if, at the end of the universe, as matter cools and energy thins, the laws could allow the flow to turn backward. But even if the cosmos eventually folds in on itself, the beings inside it would experience that collapse as forward again. The arrow is not an external compass. It's built into the way memory, matter and motion intertwine. Wherever entropy increases, time moves on. There's another arrow too, not physical but psychological. It points the same way. You can feel it when you watch a sunset and know the light won't return in quite the same hue, or when you close a door and sense that a moment has passed irretrievably behind it. That awareness is the human version of entropy, the knowledge that change is constant and that each instant once lived becomes part of the universe's permanent archive. And yet, within that one-way flow, we build meaning. We take photographs, write songs, tell stories, small acts of defiance against impermanence. We can't stop the tea from cooling, but we can remember the warmth it gave. Maybe that's what consciousness is for, to give shape and significance to the inevitable spreading of time. You might wonder if entropy defines the arrow. Does it also define time travel? Could we ever swim upstream, make entropy decrease, and see the past again? In principle, Nothing in the microscopic rules forbids it. But the odds are so vast that the universe itself would rather collapse than replay. The arrow is stitched deeply into the fabric of probability. To go backward would mean not just reversing one teacup or one heartbeat, but every interaction in every corner of existence. It would require every atom in the cosmos to agree to move the other way. That's why time travel to the past remains, at least for now, a beautiful impossibility. Still, the arrow isn't cruel. It gives us direction, progression, and story. Without it, all moments would stack together in silence. With it, the universe has melody, from the first flare of light to the slow cooling of galaxies, from the beginning of a breath to its end. Entropy writes the music, and we are the notes passing through it. So, the next time you watch steam drift from your tea, you might think of it as more than heat escaping. It's the universe marking its rhythm, the gentle pulse that lets everything change. Time doesn't rush, it exhales, and within that breath, we live. From here, the story opens into a new kind of wonder, the realization that this flowing, irreversible time can stretch and bend. Some clocks tick slower, some faster, and the universe keeps time differently in every place. Our quiet exploration now turns toward those hidden experiments and the travelers who have already touched the edge of tomorrow. High above Earth, where the air thins into silence and the sky deepens into velvet black, there are people who have already travelled into the future, not in dreams or fiction, but in the quiet precision of physics. They didn't step into glowing machines or open wormholes, they simply orbited our planet. Yet when they came home, their clocks, and their bodies, had aged just a little less than ours. It's one of those discoveries so subtle it almost feels magical. The idea that time can slow down for one person and not for another sounds like fantasy, but it's a measured truth. The story of this strange reality begins more than a century ago, when Einstein realized that time is not a universal rhythm ticking evenly across the cosmos. It bends and stretches depending on how you move through space. The faster you go, the slower your clock runs compared to someone standing still. It's not just mechanical clocks that slow. Your heartbeat, your breathing, your very thoughts all join in the delay. Imagine two twins. One stays on Earth, the other boards a spacecraft that races through the stars. The travelling twin moves so quickly that from the viewpoint of Earth, time on the ship begins to pass more slowly. When the traveller returns, both are older, but one has aged less. This isn't a story of magic or illusion. It's the twin paradox, one of the simplest ways to see that motion and time are inseparable. Of course, no one can yet move near the speed of light, where the effects would become dramatic. But even at the modest velocities of orbiting astronauts, the difference can be measured. Take Sergei Krikalev, the Russian cosmonaut who spent 803 days in space. Over those long months circling Earth, his body moved at roughly 28,000 kilometers per hour. Because of that, time ran fractionally slower for him than for those on the ground. When he finally returned, he was about 1/48th of a second younger than he would have been if he'd stayed home. It's a tiny sliver, less than the blink of an eye, but it's real. The universe had quietly gifted him an extra moment of life. The same effect appears on an even smaller scale here on Earth. In the early 1970s, physicists named Haffley and Keating carried precise atomic clocks aboard commercial airliners. They flew them eastward and westward around the planet and compared them with identical clocks left at rest. When the planes landed, the moving clocks disagreed with the stationary ones by a few billionths of a second. The faster you move, the more time eases its pace. You might not notice it, but your own smartphone relies on this principle. The global positioning system, the satellites silently circling above, keeps track of time with astonishing precision. Yet their clocks would drift badly if engineers didn't correct them for relativity. Because they're moving fast and farther from Earth's gravity, each satellite's time ticks differently than ours. Without those corrections, your map app would place you kilometers from your true location. Every moment you check directions, you're using a network of orbiting time travelers to find your way home. There's a kind of poetry in that. Our navigation through space depending on the warping of time itself. But it also reveals something profound about how the universe works. Space and time aren't separate. They're woven together into one fabric, so that tugging on one side, by moving fast or by standing in a gravitational field, changes the other. Gravity too slows time. A clock near the surface of Earth runs slightly slower than a clock on a mountaintop. You might not feel it, but it's there, measurable with the right instruments. The cause is simple to imagine. When you climb away from the planet's pull, you step into a region where space-time is stretched a little thinner. The seconds there have more room to unfold. For astronauts, both effects, motion and gravity, intertwine. Their great speed slows time, but being farther from Earth's gravity speeds it up again. The result is a delicate balance. At the altitude of the International Space Station, the slowing from speed outweighs the speeding from distance, so overall they experience a net loss of time. When they return, they've travelled ever so slightly into the future. You might wonder, how can we be sure? Scientists have measured it directly. They send synchronized atomic clocks aboard rockets and satellites, then compare them to those on Earth. The results match the predictions of relativity with stunning accuracy. Time dilation isn't a metaphor, it's a fact. Small, steady, and everywhere. But beneath the equations, there's a quieter beauty. Think of time as an elastic thread. When you move slowly, it stays relaxed, unwound. When you move faster, the thread stretches and thins. You feel no difference. Your heartbeat and breathing remain steady. But to an observer watching from another place, your seconds lengthen. Motion, in essence, is a way of stretching the fabric of existence. It's a humbling idea. Time is not something absolute, but something personal. Each of us carries our own rhythm of seconds, set by our position and speed in the universe. You are, at this moment, aging at a slightly different rate than someone on the other side of the planet, or even than your own feet, which sit closer to Earth's centre than your head. The difference is microscopic, but it means there is no single now that applies to everyone. Every point in space has its own private clock. If you could hover near a black hole, the effect would become dramatic. The immense gravity would slow time so much that a few minutes near the event horizon, the boundary where nothing escapes, could equal years for an observer far away. From your perspective, your watch would tick normally, but to distant eyes, you'd appear almost frozen. Even light would crawl upward from you, stretched thin and red as it fought to escape. It's one of the strangest predictions of relativity, and one of the most beautiful. When Christopher Nolan's film Interstellar portrayed astronauts aging more slowly near a black hole, it wasn't imagination alone. Physicist Kip Thorne, who advised the film, calculated that the scenario could truly happen under the right conditions. In a sense, it's a doorway into the future that nature herself has built. No machine required, just gravity deep enough to hold time in its hands. These effects remind us that the universe isn't a rigid grid, but a living fabric, supple and full of texture. The seconds that pass in your room aren't the same as those passing in orbit or near a distant star. Time, like sound, has tone and rhythm. Each place sings its own tempo. The astronaut who came back younger didn't cheat death or rewrite history. He simply moved through space-time along a slightly different path, one that curved just enough to let his moments unfold more slowly. And when he looked back at Earth, a pale blue light spinning far below, he was seeing the future of everyone he'd ever known. If we continue along this path, we'll find that these small ripples in time hint at something greater, a way not just to drift forward more slowly, but to imagine folding time itself. The dream of travelling beyond the present might begin with a rocket, but it reaches much deeper, into the geometry of the universe, and the imagination of the human mind. Imagine you're standing on the shore, watching the tide come in. Each wave reaches forward, curls, and then falls back again. If you could somehow step into the rhythm of those waves, not the surface, but the deep pull beneath, you'd feel something slow and deliberate, as if the ocean were breathing. That's what gravity does to time. It stretches it, softens it, and makes every second move at its own unique pace. Einstein once described gravity not as a force, but as a kind of geometry, the way mass bends the space and time around it. To picture it, imagine a wide sheet of fabric stretched tight. When you place a heavy ball in the center, the fabric dips. Smaller objects rolling nearby curve toward the depression, not because they're being pulled, but because the surface itself is shaped that way. In the same quiet way, Earth doesn't pull the moon. The moon simply follows the bend in the fabric created by Earth's presence. Now here's the part that feels almost magical. The bend in space also means a bend in time. Where the fabric dips, the seconds lengthen, not metaphorically, but truly. Clocks sitting deep in a gravitational well tick more slowly than clocks higher up. On Earth, that difference is small but measurable. A clock at sea level runs just a fraction of a second slower than one perched on a mountain peak. You could say the mountain lives in a slightly faster world. To make sense of this, think of light as your most honest timekeeper. A beam of light always travels at the same speed no matter where it goes. But when it passes through a region of stronger gravity, the space it moves through is stretched. To someone watching from afar, it looks as though the light has slowed. If you could listen carefully enough, you'd hear it hum in a lower tone, the way a stretched string vibrates more slowly. Time itself is that string. Gravity tunes its music. This isn't just theory. Scientists have watched it happen. In 1959, a pair of physicists named Pound and Rebker set up an experiment inside a tall Harvard tower. They measured how tiny packets of light, called photons, changed frequency as they climbed from the basement to the roof. The light that rose upward lost energy. Its waves stretched just a little, exactly as Einstein predicted. It was proof that gravity drains time's momentum ever so slightly. You might wonder what this means for the world around you. The truth is, you experience it constantly without noticing. Every time you climb a hill, ride an elevator, or fly in an airplane, you enter a region where time runs just a hair faster. Meanwhile, deep inside Earth's crust, time runs a bit slower. Even your feet experience more gravity than your head, so your toes are living the tiniest bit behind you. You'll never feel it. The difference is far smaller than the blink of an atom, but it's there, whispering quietly beneath every heartbeat. Astronauts feel it more strongly. When they orbit Earth, they balance between two competing effects. Their great speed slows time down, but being farther from Earth gravity speeds it up. The two nearly cancel, but not perfectly. The balance leaves them returning a few microseconds younger than they would have been on the ground. The same principle means that GPS satellites must be constantly corrected. Their onboard clocks, freed from Earth's stronger gravity, tick faster than ours by about 45 microseconds each day. Without adjusting for that difference, your map would think you were kilometers away from where you stand. The universe demands precision, even for something as gentle as a whisper in time. You can see this dance between gravity and time most vividly near the edge of a black hole. Picture a star so massive that when it collapses, its gravity becomes a bottomless pit in space-time. The closer you get to the event horizon, the invisible boundary where escape becomes impossible, the slower time flows. For a distant observer, you would appear to move slower and slower until you seemed frozen. But to you, nothing feels different. Your watch ticks normally, your heart beats as it always has. Only from far away would someone see you pause forever, a figure suspended just above the darkness. It's a haunting idea, but also strangely serene. A black hole is the ultimate clock marking the extremes of Einstein's universe. For those who fall in, time and space trade places, What once was movement becomes stillness. What once was still becomes motion. It's less a destruction than a transformation, where the meaning of moment itself dissolves. On a gentler scale, this same principle shapes the cosmos we inhabit. Time runs more slowly inside galaxies, where gravity is stronger and a little faster in the empty spaces between them. Even the universe's great expansion, the slow stretching of the cosmic fabric, has a tempo set by gravity. The denser the region, the slower its internal clock. So, in a way, the cosmos itself hums with many rhythms at once. Every cluster of stars, every planet, every beating heart plays its own measure in the grand symphony of space-time. Einstein's insight changed not only how scientists understood gravity, but how humanity understood itself. It revealed that time is not a single thread winding evenly through creation. It's more like a woven tapestry of countless threads, each pulled tighter or looser by the weight of the worlds around them. You don't move through a static timeline. You live within a constantly shifting web. Every breath, every step slightly changes your position in that invisible architecture. The next time you feel gravity holding you down, pressing you gently toward the floor, keeping your cup steady on the table, remember that it's not just pulling on your body, it's pulling on your seconds too. Your moments are a little longer here than they would be high above, in the light thin air where satellites drift. Gravity is the quiet sculptor of time, moulding each instant according to its touch. It's astonishing that something so familiar, so constant, can also be so strange. We live inside gravity's embrace from birth to death, yet only in the last century did we realize it shapes not just our path through space, but our passage through time itself. The universe keeps its own schedule, different for every star and every observer, and in that relativity, in that diversity of clocks, lies the secret to why no two perspectives of reality are ever quite the same. As we drift further into our story, we'll see how this curvature of space-time becomes the foundation for deeper mysteries, bridges that might fold the distance between moments, shortcuts not only through space but through time itself. The path now carries us toward the dreams of physicists and storytellers alike, the possibility of stepping off the steady line of time and finding a way back. It was the summer of 1941, and the thin mountain air of Colorado shimmered beneath a wide blue sky. High above the valley, two physicists, Bruno Rossi and his student David Hall, unpacked a set of instruments that looked almost too delicate for the rugged landscape. They weren't chasing stars or lightning or storms, they were chasing time itself. At the summit of Mount Evans, they built a small wooden hut to shelter their detectors. They were studying strange particles called muons, tiny messengers born in the upper atmosphere when cosmic rays strike air molecules. Muons live very briefly, only a few millionths of a second before they decay into lighter particles. According to simple logic, none should have survived the long fall to the ground. They move near the speed of light, but even that isn't fast enough to outrun their own brief lifespans, and yet detectors at sea level were catching them by the thousands. Rossi wanted to know how. He climbed high into the thin air where the particles first appeared to measure their numbers. Then he measured again near the base of the mountain. What he found seemed impossible. Far more muons reached the ground than any classical calculation could allow. Somehow, their internal clocks were running slower than expected, giving them more time to live. At first, it sounded like fantasy, but it was the universe's first undeniable proof that time itself could stretch. The muons racing through the sky at nearly the speed of the light experienced seconds differently. From their perspective, their lifetimes were still short. Those few millionths of a second felt perfectly normal. But from ours, on Earth, their clocks had slowed. Time for them had dilated, opening just enough for them to reach us. Einstein's equations had predicted this decades earlier, but Rossi's mountain gave the theory breath and pulse. Here, on a quiet ridge surrounded by alpine wind, a handful of cosmic particles had revealed the elasticity of time. If you were one of those muons, your world would be very strange. Looking down toward Earth, you'd see the distance to the surface shrink dramatically, the atmosphere compressed by your great speed. From your point of view, you'd cover only a short distance before disintegrating, a journey lasting exactly as long as your nature allowed. Both stories, the one told by the muons and the one told by Ross's instruments, are true. They coexist perfectly in the geometry of space-time. Time and distance warp together to preserve the harmony of light's constant speed. That idea that both perspectives are real is one of the most beautiful aspects of relativity. It means there isn't a single, universal stage on which all events unfold. Each observer, each traveller, carries a private version of time woven into their own path through the cosmos. The universe doesn't argue about which is correct. It simply lets every viewpoint exist simultaneously, like verses in a poem written from different angles. Rossi's mountain experiment wasn't the only confirmation. Years later, scientists built particle accelerators, enormous rings that spin subatomic particles to nearly light speed. Inside these machines, muons live longer by exactly the same ratio Einstein predicted. Their internal clocks slow as they accelerate, proving again and again that time is flexible, responsive, alive. Even atomic clocks, the most precise instruments ever made, confirm it daily. When flown around the world on aircraft or placed on fast-moving satellites, their ticks drift relative to clocks on the ground. Engineers must constantly adjust for this drift. Without doing so, our communication networks, global navigation systems, and scientific observations would slide out of sync within hours. Modern civilization, without realizing it, depends on relativity just to stay on schedule. There's a quiet satisfaction in that thought. Every time you use a phone, drive with GPS, or check the time on a satellite-fed signal, you're relying on Einstein's gentle rearrangement of reality. That time bends with motion and gravity. That seconds are never quite the same everywhere. But beyond the science lies something more personal. Rossi's mountaintop story reminds us that discovery often begins with curiosity, not grand technology. A few detectors, some careful reasoning, and a willingness to climb high enough to listen to the sky, that was enough to uncover one of the universe's most profound secrets. It's a reminder that truth doesn't always require noise or spectacle. Sometimes it appears in the hush of thin air, in data scribbled on a notebook page, in the patience of those willing to watch and wait. The beauty of that experiment is also the humility it teaches. The universe doesn't bend for us, we bend within it. Our perception of time, so firm, so comforting, is just one local rhythm in a cosmic symphony. To move fast or fall deep into gravity's arms is to join another tempo, another verse in that endless composition. Think of time as a soft fabric stretched taut across the stars. Every motion, every heartbeat, every falling muon makes the slightest ripple. The universe doesn't mind these ripples, it welcomes them. They're what make existence dynamic and alive. Without motion, time would have no texture. Without relativity, it would have no music. The thought can be dizzying, but it's also tender. When Rossi stood on that Colorado summit, perhaps he looked up between measurements and felt something beyond equations. The awareness that even the smallest particle carries a secret of the cosmos, that the ordinary flow of seconds hides infinite variation. The same sunlight warming his hands had begun its journey 8 minutes earlier from the surface of the sun. Even light, the fastest traveller, carries the marks of distance and delay. And so, as the mountain wind brushed past his instruments and the thin air whispered through the pine needles, Rossi had, in a sense, touched eternity. He had shown that the ticking of clocks, the beating of hearts, and the decay of cosmic particles all share one truth. Time is not uniform. It's a living field, responsive to where you stand and how you move. That discovery transformed physics, but it also reshaped how we think of existence. If time can slow and stretch, then it isn't a single universal stream, but a mosaic of overlapping moments, each of us drifting along our own quiet current. It makes the idea of time travel, in a small way, something we already do. Every astronaut, every satellite, every speeding particle is proof that the future and the past are not fixed walls, but directions we can gently lean into. From here, the story begins to widen again. We've seen time bend and slow. Now we'll see what happens when the universe itself bends enough to connect distant points. The path ahead leads into tunnels of theory and imagination, bridges called wormholes, where gravity and geometry twist together to form the faint outline of travel, not just through space, but through time itself. Every morning you wake up and unknowingly travel through time, not in leaps or jumps, not in flashing light or rippling portals, but quietly, gradually, the way rivers move, the way shadows stretch as the day turns toward evening. You, me, everyone. We're all time travelers, carried gently forward by the same current. The difference is, some travelers move just a little faster, and some a little slower. This isn't poetry, it's physics. The moment you move, even by a fraction, time begins to slip differently for you than for someone standing still. Walk across the room, drive your car, fly in an airplane. Each action bends time's rhythm ever so slightly. The change is microscopic, far too small to feel, but it's there, written into the structure of reality. You're never living in quite the same second as anyone else. The satellites orbiting Earth experience this dance constantly. High above us, about 20,000 kilometers from the surface, dozens of small machines circle the planet at incredible speed. They are the keepers of our global time, the GPS network. Each carries an atomic clock so precise it can measure a tick as short as 1/1000th of a second. Yet, because those satellites move fast and sit higher in weaker gravity, their clocks drift relative to ours on Earth. Without constant adjustment, the system would lose accuracy by kilometers each day. Imagine asking for directions and finding yourself standing on the wrong street because time itself disagreed with your location. To correct this, engineers program the satellites to compensate for both effects: motion, which slows time, and altitude, which speeds it up. The result is harmony, a system that depends on relativity to tell you where you are. In a quiet way, every navigation app is a small demonstration of Einstein's universe at work. It's strange to think that an idea once considered abstract philosophy now lives in your pocket, guiding you to the nearest cafe. We built machines that orbit Earth, not realizing we were also building the first working proof that time is flexible. In a sense, we've already tamed a fragment of time travel, not the kind that takes us centuries ahead or back, but the kind that keeps us synchronized across a planet that refuses to share a single clock. Even your body, in its own gentle way, participates in this dance. Your head experiences slightly less gravity than your feet, so the seconds near your skull pass a bit faster than those at your toes. Over a lifetime, the difference adds up to a tiny fraction of a second, barely measurable, yet it's there. The same happens between mountaintops and valleys, between airplanes and runways, between astronauts and the ground they orbit. The universe doesn't tick in unison, it hums in chords. You can think of this harmony as a cosmic orchestra, where each instrument, each clock, each observer plays its own rhythm. Sometimes the notes align, sometimes they drift apart, but together they create the melody of space-time. This music is constant, invisible, and everywhere. It's what allows galaxies to spiral, planets to orbit, and us to live out our lives in a steady, predictable rhythm. And yet, relativity means that predictable is only an illusion we agree upon. In truth, there is no single universal now. The second you experience while reading this sentence is not the same second experienced by someone on Mars, or even by a bird gliding through the air above you. distance and motion warp the meaning of simultaneity. Two events that seem to happen together from one perspective may not from another. Time, in other words, is local, personal, intimate. It belongs to you and to your path through the cosmos. Sometimes, when people first hear this, they imagine chaos, a universe with no shared moment. But the beauty lies in how smoothly it all works. Every perspective, every clock, fits perfectly into the larger pattern. Like threads in a tapestry, they may twist and stretch, but the picture remains whole. That's the genius of Einstein's insight. Relativity doesn't make reality uncertain, it makes it relational. Everything stays consistent when seen from within its own frame. The universe doesn't lose order, it gains connection. If you could see time painted across the stars, it would look like a landscape gently sloping and curving, deeper near massive planets, shallower in open space. Light would follow those contours, bending gracefully, while the ticking of clocks would slow or quicken like water flowing over hills. Our technology, without meaning to, maps this landscape every day. Each signal bouncing between ground stations and satellites, each digital timestamp corrected for relativity, is like an echo tracing the shape of time's terrain. Perhaps the most touching example came from the twin study NASA conducted in 2015. Astronaut Scott Kelly spent nearly a year aboard the International Space Station, while his twin brother, Mark, remained on Earth. When Scott returned, the difference was measurable, a few milliseconds, small but certain. His cells had aged a little less, his biological clock ticked more slowly. He had, in the most literal sense, experienced time travel forward. Scott once said that space changes your sense of time completely. Days blur into one another as the station circles Earth 16 times every 24 hours. You see sunrises and sunsets in quick succession, each orbit a fresh reminder that time is as much a matter of perspective as of physics. The astronauts even adjust their schedules to coordinate with mission control, blending multiple time zones into one shared rhythm, a kind of truce between clocks. When you think about it, the Earth itself is a massive time machine, spinning and orbiting, dragging us through space-time at unimaginable speed. Every second, our planet races around the Sun at 30 kilometers per second. The solar system drifts through the galaxy moves through the universe, and through it all, time flexes and ripples. We are passengers, barely aware of the grand motion that shapes our seconds. There's something deeply comforting about realizing that time travel isn't confined to science fiction. We're already doing it, all of us, all the time. When you gaze at the night sky, you're looking backward, seeing stars not as they are now, but as they were years, decades, or even millennia ago. The light from Sirius takes 8 years to reach your eyes. From the Andromeda Galaxy, more than 2 million. Every starlit night is a glimpse into history, proof that time travel is woven into the very act of seeing. So the next time you hold your phone to check the time or watch the sun sink below the horizon, remember that you are standing in the middle of a network of clocks, all disagreeing, all correct. Time is not a single metronome striking the same beat everywhere. It's a living, shifting harmony, one that connects mountains, satellites and hearts, beating quietly across the world. And perhaps that's the most beautiful thing about it. You don't need a machine to travel through time. You already are one. A vessel of seconds flowing forward, built of atoms that remember the stars and move ever so slightly out of step with the rest of the universe. In the smallest sense, you are. Always arriving, always departing, always in motion through the unseen fabric of space-time. If we follow the thread a little further, our story will start to leave the familiar orbit of everyday life. We've seen time bend, stretch, and slow. But what if we could make it fold, bring two distant moments together? The next step of our journey leads us gently into the strange world of bridges in space-time, the tunnels that might connect one era to another, the elegant idea known as the wormhole. Imagine holding a map in your hands. the kind that unfolds so wide it takes both arms to keep it steady. You trace a finger from one city to another and sigh at the long, winding distance between them. But then you fold the paper, gently bringing the two cities together until they touch. In that small crease, the space between them disappears. In a sense, that's what a wormhole is. Not a tunnel carved through the universe, but a fold in the fabric of space and time itself. The idea was first born from the equations of Einstein and his collaborator Nathan Rosen. They were searching for a way to describe black holes, those invisible wells where gravity becomes so intense that not even light can escape. When they examined the mathematics closely, they found something unexpected. The same equations that described the surface of a black hole also hinted at another side, a mirrored region connected through a kind of bridge. Two separate points in space-time joined by a hidden corridor. Einstein and Rosen called it a bridge, though today we whisper the more poetic name, wormhole. To picture it, imagine the universe as an enormous sheet of soft fabric. Normally we think of travelling across it, from one point to another, as a journey along its surface. But what if we could bend that sheet, fold it until those two distant points touch, and step directly across? The path would be shorter, but not because we moved faster. It would be shorter because the fabric itself changed shape around us. No one has ever seen such a bridge, of course. The idea remains beautifully theoretical, but its logic is sound. If gravity can bend space, and if time and space are inseparable, then bending one should naturally bend the other. In that bending lies the possibility that the universe may have shortcuts hidden within its folds, narrow passages that connect to distant places or even distant moments. Some physicists describe wormholes as tunnels with two openings, or mouths. One mouth might hover near Earth, the other somewhere deep in space, or perhaps in a far-off era of the same universe. If one mouth experiences time differently than the other, then walking through could be more than travel across space. It could be travel across time. The geometry would allow it. The difficulty, as always, lies in keeping such a bridge open. Left to itself, a wormhole would collapse faster than light could pass through it. Gravity's own pull would pinch it shut. To hold the tunnel open, you'd need something that resists gravity, something that pushes instead of pulls. The equations suggest a peculiar kind of energy could do this, one that has negative pressure. Scientists call it exotic matter, though no one is sure if it truly exists. You could think of it as an anti-gravity fabric, a strange shimmering presence that stretches rather than compresses. It would act like scaffolding, holding the tunnel wide enough for light, or maybe even a traveller to pass through. To most of us that sounds like the language of science fiction, and yet the universe often surprises us. Physicists have already found traces of negative energy in a laboratory setting, in the faint vacuum between two metal plates. The energy that lingers there is less than nothing, a small deficit, as though the fabric of space itself were sighing inward. It's unimaginably weak, but it proves that nature allows negative energy to exist. Whether it could ever be woven into something stable enough to support a wormhole, no one yet knows. Still, it's tempting to imagine. A bridge through time, smooth and silent, its walls glimmering with the faint curvature of space-time. You might look into one end and see your own planet, a blue and green marble hanging in the dark. Step through, and perhaps emerge in another era, 1,000 years into the past or 1,000 more into the future. To your body, the journey would take seconds. To the outside world, it could mean centuries. But there's a price to such beauty. Even if we discovered a way to create a wormhole, controlling it would be unimaginably complex. A small disturbance, a ripple of radiation, a stray particle, could destabilize the tunnel. It could collapse, or worse, stretch into something chaotic, tearing instead of folding. In that sense, wormholes feel like dreams the universe protects from overuse. They're possible on paper, perhaps even glimpsed in theory, but too delicate for the clumsy hands of civilization. And yet the concept carries a quiet poetry. Every connection, every path through space-time is also a reminder of how distance is not an absolute thing. Separation, whether between stars or seconds, might just be perspective. The same fold that joins 2 points in space could also join 2 moments in time. The difference between here and there, or now and then, could be thinner than we imagine. There's a comforting echo in that thought. It suggests that the universe might be far more connected than it appears, that the divide between the past and future could one day be crossed not by force, but by understanding. And perhaps, in some quiet corner of reality, the fold already exists. You can almost picture it, a field of stars bending inward, space itself dimpling like silk under an unseen hand. The tunnel opens, faint and transparent, a reflection of light curving through darkness. At one end, the present. At the other, the long echo of what has yet to be. A traveller steps forward, feeling no motion at all, and emerges on the other side into a different night sky. Older or younger, but still under the same cosmic breath. For now, wormholes remain mathematics and metaphor, but they also carry a lesson that lingers beyond equations. They remind us that reality may not be as linear as it seems. Perhaps time is not a wall we must march across, but a surface we might someday fold, gently, like a map, until the distance between was and will be vanishes altogether. And if that ever happens, if one end of such a bridge ages differently than the other, if one mouth drifts into the future while the other lingers in the past, then maybe, just maybe, the universe has already built a door between tomorrow and yesterday. We just haven't learned to see it yet. If we follow this thought a little further, the fabric grows stranger still. What happens when gravity doesn't just bend or fold, but spins? What if space itself begins to twist, dragging time around with it like syrup stirred in a cup? Our next quiet exploration turns to those cosmic whirlpools, to black holes that rotate like gyroscopes, and to the theoretical machines that could make time curl back upon itself. If you've ever stirred honey into a cup of tea, you've seen something simple and beautiful, the liquid twisting into a spiral, drawing everything around it into a slow whirl. Space behaves the same way near certain kinds of black holes. Their gravity is so powerful, and their spin so immense, that they drag space-time itself into rotation. Imagine the universe as a calm pond, and a black hole as a whirlpool that not only pulls matter inward, but makes the very water of space turn with it. This is called frame dragging, though the term hardly captures its poetry. In these places, time itself doesn't flow straight. It circles. The first hint of this came from Roy Kerr, a New Zealand mathematician who in 1963 found a new solution to Einstein's equations, one that described not a simple, motionless black hole, but a spinning one. Instead of collapsing into a singular point, the rotation stretches the hole into a flattened sphere, a little like a spinning coin. Around it lies a region called the ergosphere, a zone where nothing can stand still, where space-time itself swirls faster than light could ever move. Anything entering that region must spin along with it, swept into a cosmic dance from which escape is nearly impossible. To someone watching from a distance, this might look like a storm made of time. Imagine standing near the event horizon, the invisible boundary beyond which no signal can return, and watching the universe outside speed up. The faster you spin, the more those outer seconds accelerate, until hours pass in moments, days in heartbeats. In a way, every rotating black hole is already a kind of time machine, a natural experiment in how motion and gravity can twist duration into strange shapes. Physicists later realized that the geometry of such a spinning spacetime could allow something extraordinary: closed loops in time. If you travelled carefully around the black hole, avoiding its deadly centre, you might find a path that leads you not outward, but back to where and when you began. In the language of relativity, it's called a closed time-like curve, but you can think of it as a cosmic loop, a trail through the universe that folds time into a circle. Of course, this is the sort of possibility that keeps physicists awake at night. The math doesn't forbid it, but reality might. The enormous energies near a black hole would shred anything made of atoms long before it completed such a loop. Still, the idea persists, quietly whispering that the laws of nature, while strict, aren't always absolute. They bend like light near a massive star, leaving just enough space for imagination to enter. One of the most vivid extensions of this idea came from a man named Frank Tipler. In the 1970s, Tipler imagined a cylinder of ultra-dense matter spinning close to the speed of light. If it were long enough and fast enough, it could, in theory, twist space-time around its length like a ribbon. A spacecraft following the right trajectory around this spinning column could enter a loop circling back to its own past. Picture it like this: a vast metallic column stretching beyond sight, rotating so fast that it drags the nearby universe along with it. Time near the surface would not simply pass, it would spiral. Step too close, and you might find yourself circling not only through space but through history. The thought is breathtaking and a little terrifying. To make such a cylinder would require energy beyond comprehension, more than all the stars in a galaxy could provide. Even if we could build it, the slightest imperfection could tear the structure apart. And yet, the dream lingers because the math says maybe. Even a maybe is enough to keep curiosity alive. Scientists have always lived in that small space between impossible and improbable. There's something beautiful about the way equations can suggest worlds we'll never reach. And still, we imagine them. The deeper meaning of Kerr black holes and Tipler cylinders isn't that we'll someday ride them like elevators through time. It's that nature allows such shapes to exist, at least on paper. The universe, for all its order, still has corners where geometry flirts with paradox. A spinning mass can make time itself swirl, and in that swirl, possibility appears. If you look at images from the Event Horizon telescope, the glowing rings of light around real black holes, you can almost sense this rotation. The bright arc is light from one side of the disk, whipped toward us by motion. The dark heart at the centre is the shadow of time slowed nearly to a stop. Each photon that escapes has danced along space-time so distorted that the idea of before and after begins to blur. The Tipler cylinder, even as fantasy, invites reflection on something deeper, that motion and gravity together can sculpt time into unexpected forms. It teaches us that the universe is not made of rigid walls, but of pliant threads. When those threads twist, they weave spirals, and in those spirals might lie the blueprint for journeys that challenge our understanding of cause and effect. But there's another truth hidden beneath the wonder. Just because something is mathematically possible doesn't mean the cosmos allows it to survive. Many physicists suspect that if a time loop ever began to form, the forces within it would grow unstable, radiation building upon itself, tearing the structure apart before paradox could take root. In this sense, the universe behaves like a careful storyteller, removing impossible scenes before they ruin the plot. Still, the image of a spinning black hole remains one of the most mesmerizing in science. A place where time and gravity perform their slow waltz at the edge of eternity. And though we may never ride such currents, we can listen to their music. Astronomers today detect ripples from these giants in the form of gravitational waves, faint vibrations in space-time that echo through the cosmos. Each wave carries the signature of rotation, the mark of time twisted into motion. It's humbling to realize that those ripples pass through us, gently stretching and squeezing space itself by less than the width of an atom. We don't feel them, yet they connect us to the most violent and elegant dances in the universe. Somewhere, two black holes may be spiraling toward each other, dragging time into ever tighter loops, and the tremor of that event brushes past Earth in silence. As we drift further into this story, we move from spinning black holes to threads even finer. Cosmic strings and white holes, the universe's strangest twins. Each offers another possible bridge, another whisper that space and time are not separate paths but one vast, flexible fabric. And if the fabric can stretch and twist and even breathe, perhaps it holds within it the rhythm of all beginnings and all returns. Imagine plucking a single hair from your head and stretching it until it reached across the entire universe, thinner than an atom, but heavy enough to pull galaxies from their paths. That is the scale of a cosmic string. Not a string of sound or music, but of space-time itself. A flaw in the fabric left over from the universe's first moments, when everything was still hot and liquid with creation. Physicists first dreamed of these cosmic strings in the 1970s, when they realized that just as cracks form in cooling glass, the newborn universe might have left behind tiny scars as it expanded and cooled. Those scars, they thought, could be infinitely long and unimaginably dense, thinner than anything we can see, yet with a single centimetre weighing as much as a mountain. Each string would be a frozen line of tension, humming quietly in the dark, holding the memory of the universe's earliest vibrations. If one of those threads passed near you, you might never notice. It wouldn't shine or give off heat, but its gravity would distort everything nearby. Light from distant stars would bend around it, creating double images in the sky, a cosmic mirage. Two separate pictures of the same star, split by an invisible strand of space-time stretched tight as a violin string. Astronomers have searched for such patterns for decades, scanning the heavens for the telltale doubling of galaxies, the faint shadow of a cosmic thread. The mathematics behind these strings suggests something breathtaking. If two of them ever cross paths, they could twist together, forming loops that might warp space so intensely that time could join the curve. Imagine two taut cords snapping against each other and tangling, the vibration sending ripples through the universe, waves of gravity itself. In those brief instants, the geometry of space-time might be pushed into shapes we can barely describe, folds, bridges, or even small temporary wormholes. Of course, all of this remains speculative. No one has seen a cosmic string, and they may not exist at all. But their imagined presence reminds us of how flexible the universe truly is. What we call space isn't empty. It's a dynamic fabric capable of stretching, twisting, and even singing. The faint hum of gravitational waves detected on Earth, those tiny ripples from colliding black holes, could be seen as the faint notes of this cosmic music. Each frequency carries the signature of a universe still trembling from its birth. If cosmic strings represent the scars of creation, then white holes could be its exhalation, the mirror image of black holes. A black hole draws everything inward, light included, until nothing can escape. A white hole, if it exists, would do the opposite. It would only expel. Matter and energy would stream outward, unable to enter. It's a concept that sounds like science fiction, yet it arises naturally from Einstein's equations. For every mathematical description of a black hole, there exists a time-reversed twin, a place where the arrows of motion and entropy point outward instead of inward. Picture it like a fountain in space-time. A black hole is the drain, a white hole the spout. If they were connected, one might imagine matter falling into a black hole in one region of the universe and erupting from a white hole somewhere else. It's a dizzying thought. What disappears in one corner of creation could reappear in another, reborn as light. Some theorists have speculated that the two might even form the ends of a wormhole, a single bridge threading through space-time. In that view, every black hole could be an entrance, and every white hole an exit. What vanishes beyond the event horizon might not be lost forever, but merely translated elsewhere. If so, the universe could be breathing, inhaling through black holes, exhaling through white holes, recycling matter, energy, and maybe even information in a cosmic rhythm. It's an elegant possibility, though we have no proof. A white hole would be almost impossible to detect, because anything approaching it would be flung away at near-light speed. It would appear as a sudden burst of light and then vanish, leaving only confusion in its wake. Some astronomers have even wondered if certain mysterious gamma-ray flashes, those split-second explosions seen in deep space, might be glimpses of white holes briefly waking and dying again. But beyond their physics, these ideas stir something more poetic. They invite us to see the universe as a living thing, breathing, pulsing, transforming. Cosmic strings become the nerves of creation, carrying tension and vibration. Black holes and white holes become its lungs, drawing in and exhaling energy across aeons. Every galaxy, every planet, every heartbeat on Earth could be part of that slow respiration. When we look up at the night sky, we tend to think of it as still, but it isn't. Space stretches, stars move, gravity sings its silent tune. Somewhere, far beyond our reach, a cosmic string might be trembling, or a black hole might be whispering to its unseen twin. Each moment, the universe writes and rewrites its own story, never erasing, only reshaping. It's humbling to realize that the very same equations that describe the curve of an orbit can also hint at tunnels through time and fountains of light. Nature hides her extremes in the mathematics we've already written, and each time we look closely, we glimpse something wilder, more delicate than before. If a black hole and a white hole truly form two ends of the same tunnel, then perhaps creation and destruction are not opposites, but partners. The universe would not be a machine that begins and ends, but a cycle. A great pulse of energy breathing itself into new forms. And maybe that's what we are too. Fragments of that breath, moments of awareness folded into the larger rhythm. When you next look at the stars, you might imagine the invisible filaments that hold them in their places, the unseen threads humming through space. Somewhere in that web, the cosmos may be folding upon itself, connecting beginnings to endings, inhaling and exhaling across the fabric of time. If so, then we are living in the middle of a single eternal breath. And from this thought, our story begins to turn homeward again, from the far edges of space back toward the quiet human scale of our own world. For if the universe can stretch and fold, perhaps we too have found our own way to slow the flow of time, not with equations or cosmic strings, but with faith, hope, and the simple wish to see tomorrow. Our next step leads to the human side of this quest, a gentler experiment with time, where sleep itself becomes a bridge to the future. There's a story that begins not in a laboratory filled with equations, but in a quiet hospital room in California. The year was 1967, and a man named James Bedford lay surrounded by machines that had grown too quiet. His breath faded, his pulse slowed, and then, by the ordinary definition of life, he died. Yet within minutes, doctors and technicians were rushing to fulfill his final request, to keep him from being lost to time. Bedford became the first human being to be cryonically preserved, his body cooled to a state where decay could not follow. They sealed him in a capsule of liquid nitrogen, lowering the temperature until every molecule of motion slowed almost to a standstill. In that instant, time did not stop, but it softened. For Bedford, it no longer flowed as it did for the rest of us. His heart, once a rhythm of seconds, entered a silence measured in decades. He hoped that one day, medicine and technology would learn how to wake him again, how to reverse the stillness without breaking the thread of life that had been paused. He has been waiting ever since, his story a kind of human echo of those frozen particles and stretched seconds we've followed through the cosmos. Cryonics is not time travel in the way science fiction imagines it. There's no machine, no sudden leap across centuries. It's more like pressing the pause button on a fragile physical song and hoping that someone someday can find the play button again. At its heart lies a simple idea. If decay is slowed enough, and if knowledge keeps advancing, then death might be less an ending and more a long sleep. When scientists talk about freezing life, they don't mean turning it into a statue of ice. Ice crystals, after all, destroy cells. Instead, the process uses a kind of chemical stillness, replacing the water inside tissues with protective fluids that prevent crystals from forming. It's called vitrification, from the word vitreous, meaning glass-like. The body becomes, in a sense, a translucent memory of itself, not frozen solid, but preserved in suspension, like a single note held in the air. It's easy to be skeptical. The human brain is an unimaginably intricate pattern of electrical activity, fragile enough that even brief oxygen loss can erase parts of memory. Could something so delicate survive decades or centuries of deep cold? No one can yet say. But to those who believe in cryonics, the question isn't if we can restore life, but when. They point to stories in nature, frogs that freeze solid through the winter and awaken in spring, seeds that sleep for millennia before sprouting again. The universe, they say, already knows how to keep time at bay. We simply haven't learned all its methods yet. There's something profoundly human about that hope. We've always looked for ways to outlast our own fragility, to carve stone, to write books, to send golden records into space with our voices etched upon them. Cryonics is another expression of the same longing, the wish to step outside the steady march of time, to make the present hold still long enough to see what the future becomes. It also raises questions that are almost spiritual. If time is a river, then cryonics is a shallow pool beside it, a place where the current slows and eddies in silence. Does the person who reawakens remain the same as the one who fell asleep? If centuries pass between heartbeats, does the soul notice? These aren't questions physics can answer, but they remind us that science and faith often meet at the edge of mystery. You can imagine Bedford's capsule now, resting in its quiet facility among dozens of others. Metal tanks shimmer under fluorescent light, each one a silent promise. They're labelled with names, dates, and sometimes small notes from family members who couldn't bear the final goodbye. To walk among them would feel less like entering a morgue, and more like stepping into a library of unfinished stories, each life a book waiting to be continued when the right language is finally discovered. In a strange way, the idea of cryonics echoes what we've already seen in nature's deepest mechanisms. On the smallest scales, particles slip in and out of existence, pausing between states as if time itself hesitates. Near black holes, moments stretch toward infinity, each second expanding until it could contain whole lifetimes. Perhaps cryonics is humanity's attempt to mimic these cosmic pauses, to create in the fragile medium of flesh and hope a small reflection of the universe's own patience. The ethics of it are complicated. Some argue that freezing the dead is an act of denial, a refusal to accept the natural flow of life and death. Others see it as the ultimate expression of curiosity, a way to peer beyond the limits that define our species. Both perspectives share the same truth. Cryonics is less about conquering time and more about learning to live with its enormity. Whether Bedford will ever awaken is uncertain. His body may remain preserved forever, or future generations may one day find a way to revive him. Perhaps he will open his eyes in a world so changed that his memories will seem like ancient dreams. Perhaps he will not wake at all. Yet even in stillness, his story has already achieved something remarkable. It made humanity look at time differently, not as an unstoppable river, but as a landscape we might one day learn to cross with care. In the end, Cryonics isn't just about extending life, it's about trust. Trust in knowledge, trust in tomorrow, trust that the future will be kind enough to remember us. There's tenderness in that trust and courage too. To sleep through centuries requires not arrogance, but faith, the quiet belief that life, once paused, can begin again. And maybe, in some small way, we all practice a form of cryonics each night. We lie down, close our eyes, and let consciousness fade, trusting that we'll wake to another dawn. Sleep is our daily rehearsal for continuity, our gentle experiment in restarting the world. The next time you drift off, you might think of James Bedford and the others who sleep in the deeper cold, their dreams suspended somewhere between heartbeat and eternity. To sleep through centuries, to wake in another age, perhaps that's not so different from the dreams we chase when we gaze at the stars. In the stillness between one breath and the next, time folds quietly, waiting. As we follow the path onward, the story begins to bend again, returning from human hope to the deeper puzzles of the cosmos. If time can slow, stop, or pause, what happens when it tries to loop back upon itself? Our journey now carries us toward those paradoxes, the elegant knots of logic and physics that remind us why travelling to the past may never be as simple as turning around. Every discussion about time travel eventually arrives at the same quiet crossroads, the place where imagination meets contradiction. It's where we ask the simplest and strangest question. If you could go back in time, what would stop you from changing the past? To explore that idea, let's step into a story, one that sounds almost like a fable told around a fire. Imagine a young scientist who invents a way to move backward through time. Perhaps it's a device, perhaps a natural doorway in space. It doesn't matter how, only that it works. Driven by curiosity, the traveller decides to visit a moment long before his own birth, to meet the family he's only heard stories about. He walks through the shimmer of the machine and finds himself decades in the past, standing outside his grandfather's house. But as he approaches, an impossible thought begins to take shape. What if something goes wrong? What if an accident, a single careless act, prevents his grandfather from meeting the woman who would one day become his grandmother? The result is a paradox so famous that it's become a kind of legend, the grandfather paradox. The problem is simple but profound. If the traveller succeeds in altering the past, then he erases his own existence. But if he never existed, then he could never have travelled back to make the change in the first place. The story folds into itself like a snake biting its tail. Cause and effect lose their order. The past collapses under the weight of its own logic. Physicists call this a causal loop, but you can think of it as a hall of mirrors. Every reflection depends on the one before it, and yet there is no first image, no starting point that anchors the rest. The traveller becomes both the cause and the effect, both the writer and the reader of his own story. It's a structure that works beautifully in fiction, but in the real universe, it poses a problem. Time, as far as we can measure, depends on consistency. It doesn't like contradictions. Even in the realm of relativity, where seconds can stretch and bend, the sequence of cause and effect remains intact. Drop a stone, and the ripple follows. Heat a kettle, and the water boils. Every event fits neatly into the chain that leads from before to after. A paradox like this would snap that chain, leaving the universe without a clear timeline to follow. To resolve this, physicists and philosophers have proposed different possibilities. One of the most famous is the Novikov self-consistency principle, named after Igor Novikov, a Russian physicist who suggested that the universe may prevent paradoxes automatically. In his view, you can travel back in time, but you can't change anything that would contradict your own existence. The universe, he said, is self-healing. It will always arrange events in such a way that history remains consistent. Imagine the traveller once more, standing on that quiet street outside his grandfather's house. Perhaps he stumbles, or drops the key, or simply hesitates long enough for events to unfold exactly as they always have. The result is not disaster, but inevitability. Every attempt to alter the past becomes part of the past itself. The universe allows you to act, but only within the boundaries of what's already true. In this sense, fate isn't something imposed from above, it's geometry. You can bend the path, but you can't break it. It's a strangely comforting thought that the universe guards its own coherence. Even if time travel were possible, it would never unravel the story completely. The timeline, like a taut thread, might twist and flex, but it won't tear. You could nudge the details, move a leaf, whisper a word, yet the outcome would find its way back to where it belongs. There's humour in it too. You could say the universe has its own sense of balance, like a careful editor revising a draft. No, that can't happen, it says, quietly crossing out contradictions before they take root. Or perhaps it's like a dance, where every step, no matter how spontaneous it feels, falls into rhythm with the music that was already playing. Still, the paradox lingers because it touches something deeper than physics, our longing to undo regret. Everyone has a moment they wish they could revisit, a word unsaid, a path not taken, a goodbye that came too soon. The grandfather paradox isn't just a puzzle, it's a reflection of that human ache for second chances. It asks, what if we could go back, not to erase, but to understand? Yet even that act of imagining is its own kind of time travel. Memory lets us step backward for an instant, replaying what's already happened. And like the universe itself, our minds have built-in safeguards. We can remember and reflect, but we cannot rewrite. We may dream of branching paths, but life gives us only one, a single unbroken world line winding forward through space-time. In this way, the paradox becomes less about physics and more about acceptance. Maybe the reason the universe forbids us from changing the past is that it knows how fragile the present is, how easily one alteration could unravel all the small miracles that make each moment real. A missed accident might erase a friendship. A delayed train might erase a lifetime of love. The world, in its quiet wisdom, guards these accidents fiercely. So when we look at the grandfather paradox, perhaps we're really seeing a mirror held up to ourselves. We want to believe we control the story, that with enough knowledge we could step outside time and rearrange its pages. But maybe the truer wisdom lies in learning to read what's already written, and finding meaning in its permanence. Some physicists think that if time travel ever does become real, it will happen only in self-consistent loops. Every traveller would fulfill, not alter, the events they encounter. The future would create the past, and the past would sustain the future. It would be a perfect circle, elegant and untouchable. And maybe, in a way, that's what memory already is. A loop where yesterday lives quietly inside today, shaping what we do next. We carry our own paradoxes inside us, the desire to move forward and the yearning to look back. If you listen closely, that's what the universe seems to be whispering through every paradox. That time is not a door we can open and close, but a reflection we can learn to see ourselves in. The past is not a prison, it's a foundation. It holds us in place so that we can keep moving. As we follow this path further, we'll find other loops, stranger ones, where information or even existence itself seems to have no beginning. Our next step drifts into one of the most haunting ideas in all of physics, the Bootstrap paradox, where a thing can exist without ever being created, where the mirror reflects forever but no one remembers which side was first. Imagine a story that tells itself, a melody with no composer, a letter with no writer, a gift passed from one hand to another until no one remembers where it first came from. That's the essence of what physicists call the Bootstrap paradox, one of the most quietly beautiful and haunting puzzles in all of time travel. It asks a simple question: what if something could exist without ever being created? Let's begin with a thought experiment. Picture a scientist in the future, a century from now, who discovers the lost musical manuscripts of Beethoven. Among them is one final, unfinished symphony. She studies it for years, perfects every note, and finally decides to share it with the past, sending it back through time to the year 1822, when Beethoven is still alive. The composer receives this mysterious score, copies it down, and takes credit for it, believing it to be his own work. Generations later, the same sheet of music is rediscovered, passed forward, again, until it arrives once more in the hands of the scientist who started it all. Now ask yourself, who composed the symphony? It was never created, only passed around in a perfect self-contained loop. The music exists, but its origin doesn't. The cause and the effect fold into one another so completely that they become inseparable, like a reflection that has forgotten which side is real. This is the Bootstrap paradox, named after the old expression to pull oneself up by one's bootstraps, meaning to perform an impossible act of self-creation. It suggests that certain objects, information, or even people could exist in the universe without ever having a true beginning. They're not violations of physics as we know it, at least not yet, but they stretch our understanding of causality until it begins to hum like a string drawn too tight. To imagine it another way, think of time as a grand circle rather than a line. Most of the time, we walk along that circle in one direction, from birth to death, from past to future. But if you could loop around perfectly, if the path curved so smoothly that the end met the beginning, then an object or an idea placed somewhere along that curve would have no origin at all. It would simply be. Physicists have long debated whether such loops could exist. The equations of relativity, which allow for bending and twisting of space-time, don't explicitly forbid them. Certain solutions, like rotating black holes or wormholes stabilized by exotic matter, seem to permit closed time-like curves, meaning paths through space-time that return to their own past. Within such loops, information could circulate endlessly, sustaining itself without an external source. Of course, the universe tends to resist such neat paradoxes. To create a perfect loop of causality, everything must align exactly. The timing, the geometry, the forces. A single disturbance would break the circle, scattering cause and effect back into linear order. And yet, the idea lingers because it feels almost poetic, like something the cosmos might do just once, as a kind of signature to remind us how strange and subtle it really is. When you think about it, we already encounter smaller echoes of this paradox in daily life. A word you learned long ago drifts through your mind and you can't remember where it came from. A melody hums itself in your head, and you're not sure if you heard it somewhere or imagined it. Culture itself sometimes behaves like a bootstrap loop. Ideas circulate, lose their origin, and return as if they were born anew. Perhaps time too has its own way of recycling ideas. Some philosophers have suggested that the universe itself might be a kind of bootstrap, a self-contained reality that gave rise to its own conditions of existence. The laws of physics could, in theory, generate the universe that, in turn, gives birth to the very laws that created it. It's circular logic, but an elegant one, existence feeding back into itself, forever self-sustaining. It's easy to get lost in the maze of such thoughts, but the emotional weight of the bootstrap paradox lies in its quiet implications. If something can exist without a beginning, perhaps everything we see, the stars, the atoms, even our own thoughts, could be part of a larger self-creating pattern. Maybe the universe doesn't need an external spark. Maybe it is its own cause, an infinite mirror reflecting endlessly into itself. The image brings both wonder and unease. On one hand, it suggests a kind of cosmic perfection, a universe so complete that it contains its own origin. On the other, it erases the comfort of beginnings. We like to think of life as a story with a first page. The bootstrap paradox tells us there may be stories that start nowhere and end nowhere, just circles of meaning turning softly in the dark. In fiction, these loops are irresistible. You'll find them in stories where an inventor receives blueprints for a time machine from his future self, builds it, and then sends those same plans back again. The design never had an author, but it exists because the loop allows it. In movies, it's the letter that arrives before it's written, the book that's published before it's conceived, the love that begins before the meeting ever happens. We recognise these stories because they echo something deep in us. The feeling that life itself is sometimes recursive, that our futures whisper into our pasts through memory, intuition, or déjà vu. When you experience that strange moment of recognition, when a scene feels as though it has already happened, you're touching the emotional heart of the Bootstrap paradox. It's as if time folds gently around your awareness, giving you a glimpse of its circular nature. So, what does the paradox truly tell us? Perhaps that creation and discovery are not as different as they seem. Every idea, every invention feels like something drawn from the void. Yet what if the void is simply the other side of the mirror? The act of creation might always be a kind of remembering, pulling something from the loop that has been there all along. When you look into a mirror, you see an image that follows your movements perfectly. You raise your hand, and the reflection raises its hand at the same instant. Neither leads, neither follows. They exist together, each making the other possible. The Bootstrap paradox is that mirror stretched across the dimension of time. Cause and effect no longer stand in line. They face each other, infinitely synchronized. And perhaps that's not so strange after all. Every heartbeat creates a future and remembers a past in the same motion. Every breath you take is both an intake of what was and an offering to what will be. Maybe we are all, in our quiet way, part of one great loop, a self-sustaining universe thinking itself into being. If we drift a little further along this thread, the loop begins to hum with an even stranger melody, one where attempts to change destiny only make it unfold exactly as it was meant to. Our next step in this exploration turns gently toward the paradox of predestination, where the future itself becomes the author of the past and history writes its own ending before the first line is even drawn. There's a moment deep in many stories when a character tries to change their fate, to stop something tragic, to rewrite what has already been written. And almost every time, no matter how hard they struggle, the very act of resistance becomes the cause of what they were trying to avoid. That is the essence of what physicists and storytellers alike call the predestination paradox. It is the quiet reminder that, in a universe bound by time, sometimes the future writes the past just as much as the past writes the future. Imagine a young woman who one day receives a mysterious letter. Inside, in handwriting that feels uncannily familiar, she finds an address and a warning. Do not go to the old train station tomorrow night. Disturbed, she obeys. But the next day, curiosity wins. She decides to visit the station anyway, to see what might have happened if she hadn't listened. There, among the flickering lamps and the drifting snow, she finds an old man injured on the ground. She rushes to help him, and as he takes her hand, he whispers something only she would know. In that moment, she realizes the letter was written by her future self, years later, trying to prevent this very night. Yet her act of kindness is what ensures it happens exactly as foretold. This paradox appears simple, yet it's one of the most profound riddles in the study of time. It suggests that even when we think we're changing destiny, we might only be fulfilling it. Every choice, every attempt to alter history, could be part of the larger pattern that makes history whole. The loop closes perfectly. The warning creates the event creates the warning. There is no beginning, no end, only the rhythm of inevitability. In physics, this kind of loop is consistent with the rules of relativity. Einstein's equations don't forbid time from folding onto itself, and within such folds events can influence their own causes. Yet to our minds, trained to think in straight lines, the idea feels unsettling. We're used to seeing time as a chain, one link pulling the next. The predestination paradox replaces that with a circle, where each moment simultaneously gives birth to and is born from the next. You can find echoes of this in countless stories across culture. In 12 Monkeys, a man is sent back in time to prevent a deadly plague, only to realise that his actions are the very ones that make it possible. In The Terminator, a future hero's father is sent from that same future, ensuring his own birth. In Harry Potter and the Prisoner of Azkaban, Harry saves himself with a spell he believes came from someone else, only to learn it was his own hand all along. These tales fascinate us because they reveal something deeply human, that desire to master fate, coupled with the suspicion that we never truly can. Yet the paradox isn't purely fatalistic, it also carries a kind of grace. If every attempt to change the past becomes part of the past, then every mistake and every regret also belong exactly where they should. The universe, through this lens, becomes less of a trap and more of a completed work, a masterpiece already whole, even if we can only see it one brushstroke at a time. There's something oddly comforting about that idea. It means that the future and the past are not enemies, locked in conflict. They are partners, dancing in synchrony. What you do tomorrow may already ripple backward, shaping the memories you hold today. Maybe that's why certain moments in life feel inevitable, like lines in a story you've read before. Perhaps somewhere deep within the structure of time, the script has already been written, not as destiny imposed upon you, but as the unfolding of the pattern you've always been part of. Some philosophers compare this to a symphony. Imagine listening to a piece of music. The first note might seem independent, but as the melody continues, you realise it was leading towards something, a resolution, a harmony that gives the earlier sound its meaning. If you were to play the symphony backward, it would still make sense in its own way, because every note contains traces of what follows. Time, in the same sense, might not flow like a river, but resonate like music. The present is a chord, containing both the echoes of the past and the premonitions of the future. And if that's true, then free will doesn't disappear. It just takes a different shape. We're not puppets bound to a script. We are participants in a melody that allows improvisation while still keeping its rhythm. Your choices matter, not because they change what must happen, but because they give colour and tone to the way it happens. In a self-consistent universe, even the most spontaneous decision is still part of the harmony. There's a quiet beauty in realising that time might be self-reflective, that the future, rather than being an empty road waiting to be built, could be a mirror gently shaping the present. Physicists sometimes describe spacetime as a block universe, a four-dimensional whole where every event, past and future, coexists. In such a view, nothing is lost, nothing truly vanishes. Every heartbeat, every word remains forever woven into the tapestry of being. To live inside that tapestry is not to be trapped, but to be part of something complete. Maybe that's why we find the predestination paradox so haunting. It's not just about physics, it's about trust. Trust that the path you're on, however unpredictable it feels, might already make sense in ways you can't yet see. The things that feel like mistakes today could be the threads that hold the whole pattern together tomorrow. When we dream of changing the past, we're really dreaming of seeing the whole picture, of standing outside time long enough to understand why things happened the way they did. But perhaps that understanding is something only the universe itself possesses. We, living inside the flow, can only experience it one moment at a time, like listening to a song we're still learning the melody to. So the predestination paradox becomes not a trap, but a meditation, a reminder that time might be kinder than we think, that the story of existence isn't written by us or against us, but through us. Each of us adds a note, a word, a moment of light to the grand composition. And if that's true, if the universe really does guard its own melody, then maybe that's the secret of time travel. Not to fight the current, but to listen, to trust that even the loops, the circles, and the inevitable endings are part of something larger, something that plays on long after we've stopped hearing it. As we drift from the soft inevitability of destiny, our next step leads us toward the mind of the universe itself, to a strange, almost protective intelligence woven into physics. It's the idea that time has its own immune system, that paradoxes aren't just avoided by luck, but erased by the very fabric of reality. We'll explore that next. Stephen Hawking's quiet proposition that the cosmos, like an author guarding the last page of a novel, may protect its story from ever being rewritten. Imagine sitting at a desk late at night writing the final pages of a story. The words come easily, flowing until the last paragraph, when something strange happens. The ink refuses to dry. No matter how many times you try to finish the sentence, the page stays blank. It's as if the story itself has decided that certain endings are forbidden. That, in a sense, is how Stephen Hawking saw the universe. He proposed that time might protect itself from contradictions in much the same way an author protects their manuscript from nonsense. He called this the chronology protection conjecture, the idea that the laws of physics contain an invisible editor, erasing paradoxes before they can appear. Hawking imagined what would happen if someone really did try to build a time machine. A wormhole stabilised by exotic matter, or a tunnel wrapped around a spinning black hole. According to the equations, such devices are possible in theory, but Hawking noticed something troubling. Whenever you try to form a loop in time, quantum effects, the small, jittering motions of particles, begin to explode in intensity. Radiation builds up inside the curve until it tears the structure apart. In simple terms, the closer you get to making a time loop, the more violently the universe resists. It's as if reality has a built-in safeguard, a natural no-entry sign placed at the door of every paradox. The universe, Hawking said with a hint of humour, seems to be run by a kind of cosmic censor, making sure no one writes contradictory stories into the timeline. You can imagine it like a librarian who watches over the archives of existence, quietly removing pages that would make the plot collapse. Why would the universe bother protecting itself in this way? Perhaps because consistency is the foundation of everything. If paradoxes were allowed, cause and effect would lose meaning. Light might not follow its path, gravity might not pull in predictable ways, and the delicate web of relationships that allows stars to shine and atoms to form could unravel. The cosmos is not just vast, it is precise. It values coherence over chaos. Hawking's conjecture suggests that even if wormholes or spinning cylinders could form, they would never become usable time machines. The very act of trying would summon a wave of quantum feedback, bursts of energy so intense that the tunnel would collapse in on itself. It's not that the universe doesn't allow imagination, it simply draws a quiet boundary between what can be dreamed and what can endure. Think of it as the difference between a shadow and a reflection. The equations show the possibility, a glimmer of how time loops might exist. But when those possibilities meet reality, the reflection shatters. What remains is the shadow, the hint of what could be, preserved in mathematics but erased from the physical world. In this way, the chronology protection conjecture becomes less of a limitation and more of a reassurance. It tells us that the universe takes care of its own logic, that we won't accidentally unravel time by curiosity alone. Hawking once joked that the absence of tourists from the future is the strongest evidence that time travel to the past is impossible. Where, he asked, are the crowds from centuries ahead arriving in their silver suits to take photographs of us? If they're not here, perhaps it's because the universe simply won't let them cross that line. But beneath the humour was something profound. Hawking believed that the laws of physics are not just arbitrary rules, they are the language in which the universe writes its story, and like any good story, it must make sense. Loops without logic, endings without causes, are edited out by the very structure of reality. In a sense, the cosmos is not chaotic. It's self-aware, maintaining its own narrative integrity. You can see this idea reflected even in nature's smallest scales. In quantum mechanics, when two outcomes are possible, the system doesn't collapse into contradiction. It balances itself through probabilities. The act of observation doesn't destroy coherence, it restores it in a new form. Hawking's vision extends that idea to time itself. When contradictions threaten to form, the quantum world responds by closing the loopholes, dissolving the impossible before it can take shape. There's something quietly comforting about imagining time as self-protecting. It means that existence is not fragile, even if our understanding of it is. No matter how far we stretch our imagination, through wormholes, paradoxes, or frozen sleepers waiting for dawn, the universe holds steady, its internal rhythm unbroken. It has survived supernovae, collisions, and the birth and death of galaxies. Why wouldn't it also survive the thought experiments of curious minds? Still, Hawking's idea carries a gentle irony. His entire career was spent exploring the edges of possibility, black holes, singularities, the beginning of time itself. Yet here he was, proposing that some edges cannot be crossed. Perhaps he understood that mystery itself is essential to meaning. A story with every answer loses its power. So does a universe without boundaries. If time travel to the past is forbidden, that doesn't make the dream meaningless. On the contrary, it makes it precious. The impossibility of rewriting the past gives weight to every present moment. Each decision, each act of kindness, each word spoken is irreversible and therefore sacred. We may not be able to loop backward, but we can still shape what comes next. And in doing so, we become the future's authors. In a way, Hawking's chronology protection isn't just about physics, it's about humility. It reminds us that we are part of a universe that guards its coherence the way a poet guards the rhythm of a line. Our curiosity can stretch it, test it, even bend it, but the structure holds. That structure is the reason the stars don't fall apart, the reason clocks agree, the reason time, despite its mystery, continues to flow. Maybe that's the universe's quiet gift. Protection not from danger, but from incoherence. From falling into a story that no longer makes sense. And so, in the silence between paradox and possibility, Hawking left us with something gentle, a sense that the cosmos, for all its strangeness, prefers peace over confusion. As we close this chapter, we step out of the realm of paradoxes and into something even subtler, the quantum threads beneath them. For if time protects itself on the grandest scales, what happens in the tiniest ones? Can particles, those flickering ghosts of energy, cheat time in ways we cannot? The next part of our journey drifts into the quantum world, where uncertainty replaces certainty, and where time itself begins to shimmer like light upon water. If you could shrink yourself smaller than a dust mote, smaller even than a virus or a single atom, you'd find yourself in a realm that feels more like poetry than physics. Down there, time doesn't flow like a river, it flickers, glitters, hesitates. What we call before and after start to lose their certainty. The world of the quantum is not one of clocks and seconds, but of possibilities, shimmering, overlapping, and forever rearranging themselves. Physicists once imagined that if we could see far enough inward, we'd find tiny marbles making up everything, neat, solid, predictable. But instead, we found something much stranger, particles that behave like waves, waves that behave like particles, and moments when both seem to happen at once. At this scale, time itself seems unsure which way to turn. Richard Feynman, one of the most playful minds in 20th century physics, tried to make sense of it by drawing. He filled page after page with little arrows and lines, simple sketches showing how particles move, interact, and vanish. Each line wasn't just a path in space, but in time as well. When Feynman followed the mathematics, he noticed something odd. The equations that described a particle moving forward in time looked almost identical to those describing its twin, called an antiparticle, moving backward. It was a revelation. Perhaps antimatter, the mirror substance to the matter we're made of, wasn't different at all. Maybe it was simply matter running the same film in reverse. Every electron, Feynman mused, might have a shadow self retracing its footsteps from the future to the past, the two crossing paths without ever colliding. You can picture it as a waltz on the smallest stage imaginable. One partner moves forward through the melody, the other glides backward in perfect rhythm. The music itself, quantum mechanics, keeps time for both, though neither seems aware of which direction they're really dancing. That's not just philosophy, it's built into the structure of reality. The laws that govern the quantum world are symmetrical in time. They don't prefer forward to backward. A movie of particles colliding and rebounding could play either way and still obey the rules. The direction we call forward emerges only when countless of these tiny dances add up, creating the arrow of time we live by. At the microscopic scale, the arrow quivers, and then there's the magic of quantum tunneling. In our ordinary world, barriers are barriers. A ball can't pass through a wall unless it breaks it. But in the quantum realm, particles sometimes behave like soft echoes instead of hard points. They drift close to a barrier, fade for an instant, and reappear on the other side. It's as if the universe occasionally allows shortcuts, brief permissions to do the impossible. To us, it seems instantaneous, but to the particle, it's simply following all possible paths, including the one that defies common sense. You could say the particle remembers the other side before it arrives there. It's not for knowledge, not quite, it's coherence. Every outcome exists in delicate superposition until something, a measurement, a meeting, a touch, forces the universe to choose. And in that moment, time seems to flinch, deciding which side of the mirror we get to see. This behavior is everywhere, hidden in plain sight. It's what lets the sun shine. Deep inside its core, particles called protons tunnel through energy barriers they shouldn't be able to cross, fusing into new atoms and releasing light. Every sunrise is, in a sense, the result of quantum time travel, the future warmth of daylight influencing the reactions that make it possible. There are even experiments that hint at quantum systems responding to future conditions. Not in a mystical way, but in a statistical one. The outcomes of certain particle interactions seem to depend not only on what happened before, but also on how the system will be observed later. It's as though the smallest pieces of reality don't just remember their past, they anticipate their role in what's yet to come. To the human mind, this sounds like prophecy. But to physics, it's simply symmetry. The equations of motion work both ways. The distinction between cause and effect dissolves into something softer, a conversation rather than a command. The universe doesn't say first this, then that. It whispers, both belong. You can feel the poetry of that when you watch a droplet of water ripple outward on a pond. The circles move away, but if you could reverse the film, they'd flow inward again, gathering perfectly into the original drop. The laws of nature don't mind the reversal. It's only the friction of reality, entropy, heat, the sheer messiness of the world that makes the forward version the one we live in. Quantum physics invites us to imagine what happens where that friction disappears. In the silence between one vibration and the next, the smallest building blocks of existence might flutter back and forth in time, weaving the fabric that feels, to us, like continuity. Perhaps now is not a slice of time at all, but a shimmer created by countless microscopic trips forward and backward, like a billion invisible pendulums keeping reality in balance. Even antimatter itself carries this strangeness into the visible world. When matter and antimatter meet, they annihilate in a flash of light, as if the forward and backward dancers have finally embraced cancelling each other's steps. The energy that appears is not destruction, it's reconciliation, the release that comes when opposites recognise themselves. There's something tender in that image. It suggests that the universe is not at war with itself, even in its smallest motions. Everything has its counterpart, its reflection, its returning rhythm. What we call the past and future may be less like a straight road and more like the two sides of a heartbeat. If you could stand outside time and look in, you might see the quantum world as a vast network of lights blinking both ways, flickering like fireflies on a warm night, each flash influencing the others in patterns too quick for our eyes. From those flickers, reality emerges, steady, directional, human. And so, when we say a particle remembers tomorrow, we're not speaking of prediction, but of connection. The future and the past are linked through every atom, each moment participating in both directions at once. It's this delicate exchange that makes the world solid and luminous, that lets us wake to a sunrise instead of a blur. In the smallest scales, time doesn't march. It flutters. It bends and breathes, shimmering like heat above a road on a summer afternoon. It's not straight, but alive. And if we listen closely enough, we might feel that same shimmer in ourselves, in every thought, every memory, every hope that bridges what was with what will be. From here, our quiet journey continues outward, into a vaster idea still. If time can shimmer within a single particle, what happens when countless possibilities unfold all at once? What if the universe, instead of choosing one path, allows them all to bloom? The path ahead opens softly into a garden of worlds, a place where every decision divides, not with noise, but with silence. Imagine standing at a fork in the road where the path splits endlessly ahead of you. You pause, unsure which way to go. To your left, the trail winds toward the sea. To your right, it disappears into the forest. In your world, the one you know, you choose the sea. You feel the salt air, hear the slow hiss of waves. But somewhere, in another quiet version of the universe, another you turned right and is now walking beneath green canopies of leaves, listening to the whisper of branches above. This is the strange, almost dreamlike world imagined by the physicist Hugh Everett in 1957. He was trying to solve a puzzle at the heart of quantum mechanics. When a particle exists in several possible states at once, why do we only ever see one outcome? When you observe an electron, for instance, it's as if the universe flips a coin and shows you either heads or tails, never both. But according to the equations, both possibilities continue to exist. So where does the other one go? Everett's answer was breathtaking in its simplicity. It doesn't go anywhere. It continues, but in a different branch of reality. Every quantum event, he proposed, causes the universe to divide into versions of itself. In one branch, the particle goes left. In another, it goes right. Both outcomes are equally real, unfolding in parallel. The universe doesn't choose, it multiplies. You can picture this idea not as a series of separate universes scattered like marbles in space, but as a vast interconnected garden. Each pathway a different version of history, each leaf a possibility that grew from a single stem. At every decision, at every chance interaction, the garden divides. Not with thunder or explosion, but with quiet elegance, like the unfolding of petals in slow motion. It's tempting to think of these other worlds as distant or unreachable, but in truth, they may lie right beside us, separated only by a difference in probability too small to measure. In one, you're reading this sentence on a screen. In another, you're hearing it through a recording. In yet another, you never found it at all. Every heartbeat, every atom, every flicker of thought may generate its own subtle divergence, spreading reality outward like ripples from a single stone dropped into an infinite pond. Of course, this is still theory. a beautiful one, but unconfirmed. The many worlds interpretation doesn't predict new phenomena, it simply redefines what reality means. Instead of a single, collapsing universe that picks one version of events, it gives us a calm, eternal forest where every outcome exists simultaneously. It doesn't contradict the equations, it fulfills them. To imagine it gently, think of yourself walking down a hallway lined with mirrors. With every step, your reflection multiplies. You turn your head, and infinite versions of you turn theirs too. You can see them, but you can't reach them. The hallway doesn't end, it extends into light. Each reflection is slightly different. An eyelid slower to blink, a heartbeat faster, and yet every one of them feels, at that moment, like you. That, in essence, is the many worlds view. Every version of you is as real as the one you're aware of, and consciousness simply travels along one of those paths. The others unfold, equally vivid, equally true, just beyond perception. This idea gives rise to one of the most haunting thought experiments in quantum philosophy, the so-called quantum immortality paradox. Imagine a scenario in which your life depends on a random quantum event, say, the decay of a single particle that determines whether a machine triggers or not. In the universe where the event happens one way, you survive. In another, you don't. From your perspective, though, you can only ever experience the version in which you live to observe it. The worlds in which you perish continue without you, unseen. In this way, consciousness might always find itself in the branch where it endures. It's a deeply unsettling and strangely comforting notion that subjectively, we might never experience an end, only transitions from one timeline to the next. Perhaps that's why life itself feels continuous, even through near misses and narrow escapes. It's as if, at each critical point, reality gently shifts to preserve the version that keeps observing. But the many worlds interpretation doesn't demand we take it so personally. It doesn't say we're eternal. It says that reality is vast enough for everything possible to happen somewhere. The true miracle isn't immortality, it's abundance. Every possible configuration of atoms, every possible sequence of choices, every possible version of you exists in that infinite garden. And yet the paradox remains, if all realities exist, why do we only experience one? Why don't we feel the branching, the splitting, the constant blooming of the world around us? Perhaps we do, in the subtle form of uncertainty, intuition, or déjà vu, those fleeting moments when we sense that life could have gone another way, that somewhere it already did. The philosopher David Deutsch once described the many worlds as the only interpretation that takes the equations of quantum mechanics seriously. In that sense, it's not fantasy, it's fidelity. The universe, unwilling to discard possibility, keeps every path. But to us, beings who live within time's single thread, that infinity is invisible. We move forward, one version at a time, unaware of the others walking beside us in silence. If the idea feels overwhelming, that's natural. It suggests that existence is far larger than we can ever imagine, not a line, but a lattice. Yet there's a strange peace in that too. Every loss, every missed opportunity, every door that closed in this world may have opened in another. Somewhere, another you said what you didn't say, reached where you couldn't reach, stayed where you had to leave. The universe, in its quiet generosity, gives every story a chance to be told. Maybe time never truly breaks. It just multiplies possibilities. The life you're living right now is one branch among countless others, and yet it feels whole. Because it is. Each version of you, in its own small corner of the infinite garden, feels the same fullness of experience, the same sense of being at the center of everything. And perhaps that's the secret hidden within the theory, that consciousness itself might be the thread connecting all these worlds. The awareness that asks, what if, could be the one thing that moves freely among them, the quiet observer for whom every possibility is, for a moment, true. As we drift gently forward from this garden of endless choices, our story begins to gather itself again. For even in a universe of infinite branches, the human heart searches for continuity, a way to understand, to feel connected, to find meaning in the shimmer of probabilities. Our next step explores how physics may reconcile these diverging paths, how the universe might allow paradoxes to dissolve not by preventing them, but by letting every impossible event simply flow into another stream. If we've learned anything from our long journey through time, it's that the universe dislikes contradictions, but it doesn't always erase them. Sometimes it resolves them by widening the stage. When cause and effect threaten to trip over each other, reality seems to make room, as though every impossible event simply flows sideways into another stream. This idea has gained quiet strength in recent years, as physicists revisit time travel through the lens of quantum theory. Instead of seeing paradoxes as fatal errors, they now treat them as puzzles that nature can solve with its usual grace. A handful of researchers, names like Shoshani, Wogan and Hauser, Waugh, have modelled scenarios in which a traveller could journey into the past without unravelling logic. Their equations suggest that when time loops back on itself, the universe adjusts. The outcomes change just enough to maintain consistency, while other possibilities branch away into separate parallel histories. Imagine it this way: a river splits into many channels before meeting the sea. Each current carries the same water, but the flow takes different routes. If one branch encounters a rock, it diverts and keeps going, while the others continue undisturbed. The river never stops, it simply learns to flow around obstacles. Time, in this view, behaves like that, endlessly adaptable, endlessly self-healing. Let's return for a moment to the famous grandfather paradox, but now through this quantum lens. Suppose someone travels back in time and, in trying to prevent their own birth, performs an action that would erase their existence. Classical logic collapses here. How can you do something that makes you unable to do it? But in quantum mechanics, there's no single history that must bear the burden of contradiction. The moment the action is attempted, reality branches. In one world, the event succeeds, and the traveller's lineage never continues. In another, the attempt fails, and the traveller remains. Both paths exist, each self-consistent, each complete. The paradox doesn't break the universe, it simply divides it into two harmonious stories. It's as if time has built-in escape hatches. Every time a paradox threatens to close the loop too tightly, the universe quietly slips through to another version of itself. In this way, every contradiction becomes not a wall, but a doorway. There's a deep humility in this vision of the cosmos. It suggests that reality is not a single fragile thread, but a vast weave. You can tug one strand without tearing the whole tapestry, because the neighbouring threads will always adjust, maintaining the pattern. In that light, the universe looks less like a deterministic machine, and more like a great improvisation, a jazz piece played across infinite scales, each note responding fluidly to the others. You might wonder what this means for the traveller. If they step through time and alter the past, do they ever return to the same future? According to this model, probably not. They might find themselves in a parallel stream, a world that looks the same, smells the same, feels familiar, but isn't quite home. A letter left on the table is gone. A word once said has been replaced by silence. Every small ripple has redirected the current just enough that the original branch is forever beyond reach. This doesn't make time travel meaningless. It makes it gentle. Instead of rewriting history, it becomes a kind of migration, moving not backward, but sideways. The traveller doesn't destroy the past. They create another version of it. They don't undo their story. They add another verse to the song. In this way, quantum theory softens the grand paradoxes of time. Where classical logic sees sharp contradictions, quantum logic sees superposition, a state in which multiple outcomes coexist until one is observed. If we apply that idea to time travel, we find that paradoxes may simply never be observed from the inside. The universe arranges itself so that every participant experiences a continuous, consistent story, even if the larger reality is split into countless unseen layers. It's a comforting thought. It means that even if time could twist and loop, the thread of experience, our sense of I was here, then there, then back again, would remain unbroken. The quantum world seems to care deeply about preserving coherence, not just in equations, but in stories. There's something almost compassionate about that. The cosmos doesn't punish curiosity, it accommodates it. When we press against its boundaries, trying to touch the past, to peer into futures that might have been, the universe responds not with violence, but with flexibility. It bends to include our questions, even if that means creating new worlds to hold the answers. Maybe that's what imagination really is, a faint reflection of that same cosmic tendency. When we dream of what could have happened, when we replay the moments we wish we'd lived differently, we're participating in a quiet quantum act. We're letting our minds branch, exploring parallel possibilities that feel as real as the one we inhabit. We can't step between them, but we can feel their presence, the way a shadow implies the existence of light we can't yet see. It's possible that one day, long after we're gone, someone will build a machine sensitive enough to test these ideas, not by sending people through time, but by measuring the subtle ripples that branching realities leave behind. The math predicts that in certain quantum systems, signals could echo faintly between versions of the same event, like whispers between overlapping dreams. If that's true, it means the boundaries between timelines are thinner than we think, not barriers, but membranes. And if time is truly that flexible, then every choice we make is part of something enormous. Each decision, however small, may be one of those gentle branches, another world flowering quietly beside this one. Perhaps there's a version of you who took a different path, made a different choice, and is reading a different story now. You'll never meet them, but you're connected all the same by the shared origin of possibility. So maybe the real paradox isn't in physics at all. Maybe it's in us, in our longing to return to what's gone, to touch what can't be changed, to merge all the branches of ourselves into one. Time won't let us, but it does something kinder. It lets us keep imagining. It lets us create in our minds the infinite garden that physics only hints at. And so, as our exploration nears its end, we turn from equations and paradoxes towards something quieter. The final part of this journey belongs not to particles or probabilities, but to us, the only true time travellers, walking gently through seconds that never repeat, carrying the entire universe forward with each breath. Somewhere in the dark, a clock is ticking, softly, steadily, like the heartbeat of the world. Every second it counts is a step you're taking through time. You don't need a machine or a wormhole or the energy of a star to travel. You've been doing it since the moment you were born. Every breath, every blink, every thought carries you forward second by second through the most remarkable timeline of all, the story of your own life. When physicists speak of time travel, they often mention energy, impossible quantities of it. To bend space-time enough to fold years together would take more power than all the stars in a galaxy combined. It's a reminder that the universe guards its architecture carefully. The great paradoxes and cosmic loops we've explored are wondrous, but they belong to equations written in the sky. The kind of travel we know, the one happening right now as you listen, is quieter. It doesn't distort space, it simply continues. Think of what you've already done. You've moved from the past to the present. Billions of seconds, each one irreplaceable. You've aged, learned, remembered, dreamed, Your cells have replaced themselves countless times. You've watched seasons pass, faces change, cities grow and vanish. The world you were born into no longer exists, and yet, somehow, you are still here, the witness carried forward by time's steady current. It's easy to forget how extraordinary that is. To exist at all means to participate in an unbroken motion that began at the Big Bang, a wave of time still unfolding across the universe. The hydrogen in your blood once drifted in interstellar clouds before stars gave it light. The calcium in your bones was forged in the heart of those stars before they died. Every atom you carry is older than the Earth itself. You are, in a literal and peaceful sense, made of time. So when you ask whether time travel is possible, the answer is yes. You're doing it now, and you always have been. The difference is that you can't turn around. The river flows one way, and maybe that's a kindness, because moving forward is how the universe learns. It's how memory accumulates, how experience becomes wisdom. Even so, humanity can't help but look back. We are creatures of memory. Our minds are small archives of time, filled with moments that still live, long after their clocks have stopped. When you remember your childhood, or a lost friend, or a morning that smelled of rain, you're not travelling backward. You're allowing those coordinates in space-time to echo through you. Your brain, that astonishing cluster of neurons and light, reassembles the world as it once was. The memory is imperfect, but the feeling is real. It's the universe speaking to itself in past tense. Perhaps that's why curiosity about time never fades. We build monuments and telescopes, write histories and songs, because we want to feel the thread connecting what was to what is. Every photograph, every story, every moment of wonder is a way of preserving the motion, of making time visible, if only for an instant. And then, of course, there's imagination, the truest time machine we've ever known. You can close your eyes right now and be anywhere, at the birth of the first star, or on a shoreline 1,000 years from now, watching the ocean reclaim the cities. Thought travels without engines, without fuel. A single question, what if, is enough to bridge centuries. Curiosity needs no energy source. It runs on wonder. Sometimes people ask why, if time travel were possible, we haven't met visitors from the future. There are many answers, but one of the gentlest is this. Perhaps they've learned not to interfere. Maybe the lesson of the universe, after all its ages of expansion, collapse and rebirth, is that each timeline must live its own story. The future, like a careful reader, doesn't turn back the page before the chapter is done. Or maybe the reason is simpler still. Maybe there are no travellers because there's no need. The universe doesn't recycle its moments, it renews them. Every sunrise, every birth, every act of kindness is the cosmos discovering itself again, in new form. Why revisit the past when time itself keeps creating fresh beginnings? Hawking once said that studying time is like trying to understand the mind of God. You can never hold it, but you can trace its patterns, the laws that shape every galaxy, every heartbeat. To study time is to listen to the pulse of existence, the rhythm that underlies everything from the orbit of planets to the flutter of eyelids. It's the same beat, just expressed in different tempos. And maybe that's why this journey feels both scientific and spiritual. To explore time is to glimpse something bigger than physics, something tender and personal. The arrow that carries us forward isn't just entropy and energy, it's growth, it's love, it's the quiet desire to see what comes next. You don't need to build a machine to travel through time, you already are one. Your body measures seconds with every breath, your memories preserve the past like light trapped in amber, and your imagination stretches toward the future like a bridge of thought. Every conversation, every act of learning, every simple moment of noticing the world adds another mile to the journey. So if you ever find yourself wondering where time travel ends, the answer is simple, it doesn't. It moves through you and because of you. Each step you take, each moment you experience changes the universe, however slightly, and the universe responds. You're part of its movement, an expression of its rhythm. Tonight, as the minutes drift into hours, you can rest knowing that you are exactly where time has brought you to be. You've crossed billions of years to reach this instant, from starlight to sunrise, from atoms to awareness. You are the continuation of the cosmos, its memory and its question. And when you close your eyes, you'll keep travelling, through dreams, through silence, through the quiet ticking of the world. Time doesn't stop when you sleep. It holds you gently, carrying you forward into the next dawn. Because in the end, time travel isn't about machines or paradoxes, it's about presence. The miracle of being here, now, aware of the motion that connects all things. To study time is to listen to the heartbeat of the universe, and to live, simply and fully, is to move with it. So take a slow breath, let it out. You've been travelling your whole life, and the journey, as far as we know, never truly ends. And so, we've reached the end of tonight's exploration. Whether your eyes are still open or already heavy with sleep, thank you for drifting through this story. The universe is vast, but for this small moment it has gathered itself around you. Calm, luminous, and alive. Sleep peacefully, traveller. Tomorrow the clock will start again.